Right.
Okay, so our next speaker is Phil Hwang from the University of Huddersfield, Observations of Arctic Sea Ice Flow Size Distribution, Conceptual Consideration and Model Evaluation.
Thank you so much for inviting me for the talk. And I want to recognize the Yanan Hwang is a PhD student. She spent a lot of time analyzing flow size, and also many of the parts are her work, PhD work. And also I acknowledge the Evgeny and Chris has been external advisor for Yanan's. And also Adam and Letty are providing FSD model data to evaluate. So I acknowledge them. Yeah. And I don't know if Fabian still watching this one. I don't know, but I just want to tell I'm open-minded with the log normal distribution for flow size. However, I'm going to present some of power law, so just forgive me on that. Okay, so there are two parts. First part is just to think about how we can simplify seasonal evolution of flow size. The very simple ideas came, and I tell you why we think about this one. And second part of presentation is for the FSD model evaluation. So first, please. Okay, so these are the table summarizing the so far the FSD flow size observation using a different observation, like from aerial photos, 1 meter resolution media image, optical images, and to like MODIS images. And then these are the reference, and these are the flow size range. And sometimes if you read all these reference, and some people are like even producing the flow size in area, and some people using a caliber diameters, and some people using all different parameterization. That's first to recognize. The second thing is all these studies are focused on the individual cases, like how much, what was the characteristics, what was the power behavior, and things like that. So we kind of think again and see, what about we just only be sitting back from all these things? What about we can think about what's going to be the general progress of the seasonal evolution of flow size? So that's the starting point of our research. Okay, so we first hypothesized how the flow size evolution will maybe works. And first thing is we start from the spring breakup. So spring breakup. So obviously we just disregard the winter sea ice, but if we start from the spring breakup, and then we kind of call the fracturing case. So what's the what kind of characteristic of flow size right after the spring breakup, and then we can kind of think about this transition, like what's going to be the period before the melt and after the spring breakup. What's going to be characteristic of this flow size? And then what about what kind of flow size characteristic when the significant melt started? And then there was a very simple ideas, and then so that we first look at so we use this kind of different resolution of the satellite data. So media is a declassified optical data, and then these world view images, and then these TerraSci images. And these are the locations of the images acquired for the study. To look at the fracturing, or so-called the spring breakup case, we look at these SAR images, spotlight. So it's very high resolution, less than 1 meter. So you can see because these are springtime, so you have like a backscattering inversion. So the flows looks like black, and these fracture lines looks white. So we kind of reverse the image processing. So we try to get the flow size on this right during the spring breakup. So these are the results. So what first thing kind of we see from this result is it kind of close to the exponent of 2, like in power behavior. However, there are some deviation over here in this bit. This might be something to do with some difficulty of doing image processing in this type of images. So there might be, so one encouraging thing we saw was immediately was the distribution is very close to the alpha equal 2. I come back that one later on. And another thing is we look at simple like a parameter shape vector from that's the major versus a minor axis of the flow. So these are the distribution for this from this data. And then we look at the media images, 1 meter resolution optical images, and we select the three kind of images. So which look like freshly breaking up. However, you might argue how you can prove. Say, I cannot, but we cannot follow all of this flow. However, we tried hard to find these cases. Okay, so three different cases. And then we plot the flow size distribution. And then we found, interestingly, all have a single power behavior with exponent of alpha equal 2. So that was interesting. And then we also, that actually quite kind of resounding this paper from 2015. It actually analyzed different types of images. One is from Bering Sea, Svalbard area, Kara Sea, and Weddell Sea, Antarctic, and all different resolution. It all show to alpha equal 2 power behavior. So now I think we kind of saw this kind of coincidence of this our result and their result, and we kind of asking questions whether actual initial flow size distribution from the spring breakup maybe have some power behavior of the alpha equal 2. So that's my first question I want to kind of say in this research. And then now we look at the transition period. So we also select the 6 different images, and it looks like the some time has been a while after the spring breakup. Of course, you might argue the how can you know how far from the spring breakup? However, that's what we kind of see, and from the flow rotation and things. So there might be some argument on that. However, so we think these 6 different images are representing so-called the transition period between spring breakup to before the intense melt. So we verify the it doesn't actually create the intensive network of the melt point. So we kind of verify to confirm this. And then we plot the flow size, right? The flow size. What was interesting is the up to 200, 300 meters, kind of showing a similar kind of behavior of alpha equal 2. However, the larger flows are dropping down. And we examined this one with images on spring breakup. We confirm this is not something to do with the limitation of image size. I think this is something to do with more physical reasons on that. So we might think, we kind of propose the idea about whether actually during this period, whether the breakup happening homogeneously across the flow size regions, or there might be some reason to believe any selective fragmentation from the large flows into propagating to smaller flows. And these are the shape vector distributions. Okay. I'm going to quickly move on to the melt. Just ignore the wave in this case, sorry. This is more melt dominant period. So these are when we analyze these 3 images, we consider as like an intensive melt happening during the time. And then we analyze the flow size. And what is interesting is we are like returning to a single power behavior from 70 meter to 2000 meter range. And then also flow size are more like narrow, the distribution become narrow and then close to the 1. So indicating it's more round kind of shapes of the flow size. So to confirm this melting actually happened during this time, and we had a co-located IMBs and other buoys, and confirming the since 18th of July, actually there was significant melting happening on that period. And another thing is we look at the various images, we identify actual melt-caused fragmentation cases. So we classify in 3 different cases, and in this case you can see the along the ridge there was the melt pond developed, and then suddenly about, I don't know when it happened, but about the 10 days or less than more than, it actually breaking in two in this way. And in this case there was a network of the melt pond developed, and you can see the red lines here. And then you can see how this particular flows actually are breaking up and these things. And also this case, we have this is SAR images. So you can see this gray area lines are indicating a thinner ice for the case. And then you can see later on it broken off along this line. So we believe the case we present before are very much dominated by the melt fragmentation cases. And so summarize what we actually think is the general life cycle of flow size. We know the spring breakup is a single power of alpha 2, and then we have a more selective breakup in between, and then maybe turning to the single power behavior, and then have some dipping down over here due to lateral melting. And also, if you look at the shape vector, you can see the distribution become narrow, and then getting close to the 1 in this case. And we more look into the 2 cases. One is how the melt pond behave under the melt dominant regions, and how the flow size behave in a wave dominant period. So we pick up the one case, in this case, from Beaufort in August time, and this is Bearings in April. So this is without melt. So we plot the simple histogram. You can see the kind of small flows are disappearing due to lateral melting. And then this actually, what is interesting about this wave case we saw was this kind of Aniska, she did a lab experiment, and remarkably, this distribution looks very similar to her result, and she defined as a normal distribution with a tempered power behavior. So it was quite interesting to see the good match on that one. And then we further expand this research on we identify 4 different cases of melt dominant cases in this region here. And then 3 different cases of the wave dominant cases in Bering Sea and Bering Sea. So we did that. I just want to show one kind of plot on this. Oh, okay. So these are the kind of images showing the subsection of these melt cases and versus the wave cases. So we analyze this data. And then I just want to show this one only. You can see more details on some other papers, so I present later. What was interesting to see was this y-axis was the shape vector, and x-axis is the flow size up to 200 meters. So what immediately, when I look at these plots, and then there are some kind of a distinctive difference in terms of between melt and wave. And wave tend to be the shape vector are ranging from like over larger range of the spread out in a way. However, especially in a melt season, it's kind of tend to like confine in a smaller range of the shape vector. So there might be another clue on how we can find out where the wave dominant or melt dominant flow size characteristics. And so, okay, all right. So let me see the time. Okay, Okay, so this one is a model evaluation. So we look at the 3 different models, and one is FSD version 2 wave, and CPAM FSD, and this WIP FSD. So these are from Lattice, is a prognostic model, and you can see all these, some of the information here. And then the CPAM is from Adam, and you can see the information, the prognostic model. And these are the Power model, this one. And there are many things I can talk about, but I just want to point out just one aspect of the comparison. So here, the black ones are the observation, and these are the different color indicating the different the model results. So first of all, if you look at the Power model result, and most likely like this Power WP or FSD, this is a Power model, actually shows the most close match to the observation. However, all these models showing overestimation of this is we measure the flow size in perimeter density. So it is a P indicating a perimeter density. So this one aspect is commonly showing here. The model showing a large perimeter density in a small flows, less than about 20 or 30 meters. And then we kind of reason it might be something wrong with the model. Also, it can be something wrong with our observation. So we look at the 2 different cases. One is the 1 meter resolution media data, and then coincident image with a world view image of a half meter resolution. So what is interesting is before about 20 or 30 meters, these 2 flow sizes are really matching each other. However, they start to see deviation in smaller flows. So that indicating the image resolution we're using actually do have a limitation. So this deviation here is something to do with observation as well. So, but we don't know. If we have an infinite kind of image resolution, the data with the image resolution, we might actually get close if the model is accurate. So that's the kind of point I'm trying to make here. And this is a little complicated, but I just want to point out, this is still preliminary results, so if any mistake, just forgive me. So the one thing we look at this, these are the CIS concentration versus perimeter density. These are the observation in black, and these are the CPAM, and these are the FSD version 2 wave models. So one thing was striking was and also another thing is it is blue area is a northern area, it's a southern area in this legend here. So just want to point out things. The solid the dot is indicating the southern regions over here. So when we compare the actual observation with the model, we see especially the FSD version 2 model are actually very far off from the observation. And also, if you see carefully on this, ice concentration, the perimeter density actually increased with reducing the CIS concentration, which we might expect the way. However, this shows the opposite way. And we believe this is something to do with the wave parameterization in the model, because this is the kind of showing how monthly change happening in perimeter density due to wave, in this case, in a color region. So that's one thing we're trying to more investigate on that. And the second thing I want to point out, in palm strait case, the observation happened in a northern area. So actually, in that case, we didn't see any wave effect from the model. So no wave in the model. However, we see very large large value of the perimeter density from the model, especially between, especially FSD version 2 model. So we're just wondering why it happened, why so different from the observation. but CPAM seems to be more close to the observation in this case. So, so we look at the numbers in different monthly change of perimeter density in all these different vectors. So we found out the floe welding is one of the maybe the key contribution to the difference in, but we still try to investigate on what actually happened in a way. And another point I'm trying to make is this is the kind of spring fracture, like a springtime case we presented it earlier, and we actually look at the two different prognostic model at the same kind of cases. And all seems like in terms of powder behavior, it seems like more steeper slopes showing than actual observation. So we kind of suspect maybe from the start of the spring breakup, maybe a model itself also they overestimate the flow size from the beginning. Okay, so quick point. There's no conclusion. I have a more question to ask actually. Sorry. So I think it's possible to generalize the seasonal evolution. However, the data set is very small. So I think really good to gather all the data, we reanalyze and look at this problem more carefully on that. And then what is alpha equal 2 is something to do with that, whether it's useful to. And also another question is, any selective fragmentation is still valid ideas? Is something can be think about. And another thing is whether any real difference between merit fragmentation and wave fragmentation cases. What are the difference and how we can measure this? How can we probably in the model, how can you implement in your case, I think. Yeah. And for the model evaluation, I think there's some we see overestimation in small flows. It may be related to image resolution in parts, and also the wave breakup parameterization. I don't know what's wrong with that. Maybe something to look at it. And also the maybe flow welding and maybe causing some difference in certain model and maybe related to CIS concentration in a way. I think that's it. And these are the paper. This one is published in a philosophical A, but this one is still in review, so need a little bit check on this content there. Yeah. Thank you. That's it. Yeah.
Thank you, Phil. I think there are probably many questions that your talk has raised, and I'm sure that some people have opinions on them. But I just wanted to say one thing that I noticed straight away when I saw this. In the spring breakup, okay, the shape factor was around 1.5.
Oh, okay.
You showed it.
Oh, shape factor. Sorry, sorry. I saw about alpha value. Oh, sorry.
Yeah. But they're not alpha. The shape factor was 1.5. Okay. That's broadly consistent with in-plane brittle fracture, because that would correspond to an internal angle of around 60 degrees or so. Okay. So I would say that's yet another element of evidence that brittle fracture is what's controlling the initial flow size distribution. But yeah, and what's interesting is that shape factor decreases over time slightly, okay, which is also what you'd expect if melting was starting to take place. So that could be a crucial discriminating factor looking at different fragmentation processes. And I could say more, but I think other people probably want to say more as well.
Yeah, just one thing, I remember one of the presentations, they said the aspect ratio is 1 to 3 for wave breakup. Yeah, so, but I don't know, there's something to, yeah.
Other questions?
Hi, thank you for the talk. I was curious about the comparison between Medea and I think it was Wave Worldview. Were those the same time or different years?
Okay, so the Medea data, they don't publish the time, as you know. Yeah, it's declassified, so we know the dates. and we look at the images, looks very similar. So we collect the data for the same day.
Years, same years?
No, same date.
Okay.
Same date.
Date,
Yeah.
Anyone else? Nettie? You're going to catch me out. Ladies first. Josh is so.
I guess I'll just say that for the perimeter density, it's very strongly driven by the small flows. So if you're not able to capture them that well in the observations, then that might be quite a large part of that difference in the perimeter versus concentration.
Yes.
So so you spoke of a power law distribution in our previous speaker, like Fabien spoke of a log normal. For the non-expert like me, can you address like this discrepancy or?
I don't want to address the difference. I would rather I would rather work with him, and we have all the data. We can present that way, Roman, and we can see what is true. And maybe I think it's something to do with the different fragmentation mechanism. So he mentioned about repeated fragmentation is like a wave. It's having a behavior of a log normal, but fracturing like a spring breaker case, I think probably we can consider as an instant like a fragmentation. In the case, maybe different behavior. So, but all the data is published in a Polar Data Center, so everyone can access to and have a look whether log normal or power. I don't want to go into the debate on that. Yeah, we want to see. Yeah.
Are there any last questions? Okay, I think we should thank Phil again.
Yeah.
And the other thing I want to say is that the really astute amongst you will have noticed that I chaired the session this morning as well. So I'd like to thank the speakers from this morning and the speakers from this afternoon, if I may. And we'll reconvene on time at 3:30. Danny, did you want to say anything?
Ken's chairing the next session, so okay. I just wanted to get a poll. People are interested in this. If you want, I can ask to see whether the Isaac Newton Institute will put up PDFs of the posters that have been displayed. I know because the talks are obviously being displayed, the posters are not by default. Okay, maybe if you can come up and tell me if you don't want to have your poster displayed, because I understand there may be information you don't necessarily want to have on the internet. Okay, but otherwise I thought it was probably generally